In this CPR, I'm going to go over the dielectric boundary problem from exam 2, question 9, that involves two different materials separated by a sheet of charge. So we're going to define two regions. Region A, the dielectric material on the left side for x is less than 0. Region B, which is free space on the right side for x is greater than 0. And region A has a relative permittivity of 5, and region B, being free space, has a relative permittivity of 1. And at the boundary between them, located at x equals 0, there's a sheet of free charge with surface charge density rho sub s equals 2 coulombs per meter squared. And we're told that the total electric flux density in region A is d sub A equals 4 a sub x plus 5 a sub y minus 10 a sub z coulombs per meter squared. And our goal is to determine the electric flux density for the region x is greater than 0, which we're going to call d sub b. So we can solve this by using Maxwell's equations directly instead of memorizing boundary conditions. So I'll start by sketching the setup. So the horizontal axis is represented by x, and we have the boundary at x equals 0. We have the y-axis here. And to the left of the boundary is region A, with a relative permittivity of 5, and to the right of the boundary is region B, which has a relative permittivity of 1. And at the interface, we have a sheet of surface charge labeled rho sub s. And this sheet is what creates a jump in the normal component of D, because it adds or removes electric flux right at the boundary. So to relate the tangential field components, we draw a small rectangular loop that straddles the boundary, and we apply the closed integral E dot dl equals 0. And this loop is drawn counterclockwise, which follows the right-hand rule. So if the loop's normal vector points out of the page along the positive z direction, curling your fingers around that direction gives a counterclockwise path. And we'll only consider the left and right sides of this loop, not all four. And that's because the electric field along the two short sides, these two sides, is perpendicular to the path direction dl. So their contributions are 0. Only these two sides, the longer sides, which run parallel to the y-axis, contribute. So here we have the electric field E of By, and here we have the electric field E of Ay. And from this closed integral, E dot dl equals 0, we can get that E sub Ay times the width, sorry, I forgot to label that, this will be the width W here, minus E sub By times W equals 0. And we're subtracting E sub By because it is running opposite to the direction of the loop. And so if we divide by W, we can get that E sub Ay equals E sub By, which shows that the tangential component of E is continuous across the interface. And to find how the normal component of D behaves, we can use a small cylindrical Gaussian surface that straddles the boundary. And one circular face is in region A and the other is in region B. And the cylinder's flat faces are perpendicular to the x-axis, and the curved side contributes nothing. So everything in here contributes nothing because D is parallel to the cylinder's axis. Now, we can draw our electric flux density directions. We have d sub ax here and d sub bx here. And they're both drawn pointing to the right in the positive A direction, or positive x direction. And that's because those arrows represent the actual direction of the electric flux density fields in each region, not the outward normal directions of the surface. And then when applying Gauss's law, we'll account for the outward normals separately. So we have the outward normal on the right face in region B, points in the in the positive x direction, and the outward normal on the left face in region A points in the negative x direction. So even though both d sub ax and d sub bx point right physically, their flux contributions have opposite signs because of how the surface vectors ds are oriented. And when we apply Gauss's law, the total flux becomes d sub bx times the positive s plus d sub ax times the negative s, since it's going in the negative x direction, times the free surface charge times s. Simplifying will give us, cancel out the s's, so simplifying will give us that d sub bx minus d sub ax equals rho sub s. And now we can go ahead and solve. So rearranging, we get that d sub bx equals rho sub s plus d sub ax, which equals 2 plus 4, and we know that from here, which gives us 6 in the a sub x direction coulombs per meter squared. So that's our x direction value for the B region, for the electric flux density of the B region. And now we can go back here, and we know that the electric field is equal to the electric flux density over the relative permittivity of that region. So we can rearrange this, and we'll get d sub ay over 5 epsilon naught equals d sub by over just epsilon naught. Canceling the epsilon naughts, we get that d sub by equals d sub ay over 5. We know that d sub ay equals 5, so we get that 5 over 5, which equals 1 in the a sub y direction, coulombs per meter squared. And similarly, if we instead replace this with the z-axis, it would behave exactly the same. So we can do that d sub bz equals d sub az over 5, which equals negative 10 over 5. We know that from here, which equals negative 2 in the a sub z direction, coulombs per meter squared. And now we have our final answer. You know that the total flux density, electric flux density in the B region is equal to 6 a sub x plus 1 a sub y minus 2 a sub z coulombs per meter squared. And that is our final answer for this problem. And here the normal component changed because of the surface charge, and the tangential component scaled by the permittivity ratio. And we can take away 2 key properties from this problem. This problem perfectly illustrates 2 key boundary relationships that come directly from Maxwell's equations. And one is that the tangential E continuity comes from the closed integral E dot dl equals 0. There's no net circulation of E around a closed loop, so the tangential components must match. When the materials have different permittivities, that equality in E means that the tangential components of D scale by the ratio of the permittivities. And the second one is that the normal D discontinuity comes from the closed integral D dot ds equals the free charge enclosed, which gives that the normal component of D changes by exactly the surface charge density.